Okay, welcome to the session of Linguistic Components in End-to-End ASR. My name is Thomas Scharf. I'm with 3M Health Information Systems, M Model. And together with Peter, who will introduce himself in a minute, we'll share the session. The presentations will be 15 minutes long and 5 minutes for questions. It will be a very interesting session. So, Peter?
So, hello, my name is Petr Schwarz. I'm from Brno University of Technology and Phonexia. And today we have here really diverse sessions. So we have two articles about code switching. We have an article about OE, German dialect recognition, one about new acoustic units, and we have very theoretical article about the neural network transducer, and yeah. So I would like to welcome the first speaker. It's the first article about code switching, and welcome Ondřej Klejch here.
Okay, good morning. Thank you for coming to this talk. My name is Ondřej, and in this talk I am going to present our submission to the multilingual and code switching ASR challenges for low resource Indian languages. So just to give you a quick overview of the challenge consisted of two subtasks. In the first subtask, the goal was to build a multilingual ASR for 6 Indian languages: Bengali, Hindi, Marathi, Odia, Tamil, and Telugu. And since in the blind test set there were no language ID labels, we had to also include language identification into this problem. In the second subtask was about the already mentioned code switching ASR for Hindi English and Bengali English technical lectures from YouTube. So our approach to this challenge was to use standard Kaldi recipes and try to use as much automatically crawled data as possible. We did this to compensate for the small amounts of training data, both acoustic and text data, but also to increase the diversity of the training data. We also used automatically crawled data to compensate for lack of our knowledge of Indian languages. So we did some automatic phone matching for Indian languages. So the system overview of the subtask 1 system is that our model was CNN-TDNN with language-specific outputs. It was trained with LFMI, and it was trained in 2 stages. In the first stage, we put all the data and we did multilingual pre-training. And then in the second stage, we did multilingual fine-tuning to improve the performance of the acoustic model. The language model was a standard diagram, and we used RNN language model for rescoring. So one of the biggest challenges in building models for low resource languages is that we don't have enough transcribed data. So one way how to compensate for this problem is to crawl YouTube data. But if you don't know the language, it's really hard to find suitable data. So we built an automatic pipeline that can crawl YouTube videos in any language by searching for the most common trigrams in a language model. But this can lead to some problems because we can crawl videos that correspond to different language, or we can crawl music videos. So we need to do some filtering. Our filtering pipeline is based on mean confidence, which is computed on the whole recording, and speaking rate. And as you can see from this figure, where the orange dots correspond to the videos in the target language, green dots correspond to the videos in some other language, and blue dots correspond to automatically crawled videos, there is a big difference between YouTube videos. But the main message is that we can successfully use mean confidence to filter videos in the target language from videos in other languages. And we can use speaking rate to remove some noisy videos, such as music videos. So in our approach, we use the threshold for mean confidence of 0.7 and 1.25 for speaking rate. So once we have these videos, we need to obtain transcriptions because usually there are no good transcriptions for YouTube videos. So we deal with this with semi-supervised training. We use the initial seed model trained on the provided training data to decode the videos, and then we use the decoded lattices as pseudo-labels for training. I think that it is important to stress that we use lattices, not one best pass. And this is useful because we don't need to do any confidence filtering of the transcripts. So let's look at the results. When we start with the multilingual model and we have Oracle language ID, the average word error rate is 24.9%. When we do monolingual fine-tuning, the word error rate drops to 24.2%. When we incorporate CommonCrawl data, text data, the word error rate drops to 19.3%. This is because the diversity of the text data is much larger in the CommonCrawl data. And finally, when we do RNN language model rescoring, the word error rate is 18.4%. Now, when we try to use the automatically crawled YouTube data, the initial word error rate is much higher than previously. And this is because the automatically crawled data might be mismatched from the test conditions. So to fix this problem, we do the monolingual fine-tuning using the provided training data, and that seems to help. And when we incorporate the vector language model and RNN language model, the word error rate is better than when you use only the training data. So we use this model as a submission to the challenge. And as I said, the problem is that there are no language labels in the test set. So we also had to do language identification. And we used simple heuristic based on confidence-based language identification. So let's look at an example where we try to distinguish between Marathi and Hindi speech. So we are trying to classify whether Marathi utterances were spoken in Marathi or Hindi. And the dots that are above the diagonal line are misclassified. So there is 7.3% misclassified utterances. And this can have big effect on the final word error rate. And we know that confidence in Kali models can be, the models can be overconfident. So we need to calibrate the confidence. So when we calibrate the confidence, the misclassification drops to 2.5%. And then we found another heuristic, which is based on speech ratio, where we compute the speech ratio as the duration of decoded words divided by the duration of the segment, and it seems to further improve the language identification to 1.9%. So how does this affect the word error rate? If we use only the confidence, the word error rate is 20.5. If we use calibrated confidence, the word error rate is 18.5. And if we also include the speech ratio, the word error rate is 18.1, which is really close to the Oracle language ID, which achieves 17.7. So this seems to work very well. Now, moving on to the second subtask, where we had to build a model for code switching. Again, the model was CNN-TDNN with language-specific outputs, and it was trained only with multilingual training because we found that monolingual fine-tuning didn't seem to help. This is probably because both tasks were from the same domain, so it was useful to have all data pooled together. And we used trigram language model and RNN language model rescoring. So one challenge that we tried to solve in this subtask was that the provided lexicon used language-specific units. To give you an example, English words used phoneme units, and the Hindi words used graphemes. And we thought that this might be suboptimal because same sounds might be represented with two different units in each language. So by mapping these units into one shared space, we might get some benefits. But since we had no native speaker of Hindi or Bengali, we had to do this automatically. So we devised a method to automatically crawl Wikipedia data to be able to train this phone matcher. So how do we crawl the Wikipedia data? Let's say that I want to read something about David Beckham on Wikipedia. And from the Wikipedia on the left, I can see different versions in different languages. So I can look at the English language and Hindi language. And from the website, I can automatically obtain the first name of David Beckham. Now, when I have these versions, I can use monolingual lexicons to obtain the corresponding pronunciations. And from these pronunciations, I can train phoneme matcher, which is based on joint n-gram model. The second challenge in building code switching ASR is that we need a good language model that contains terms both in Hindi, in Bengali, and English. So we need a lot of English technical terms, which might be quite rare in the normal Hindi Bengali CommonCrawl. So we need something in domain. So we downloaded subtitles of English lectures from spokentutorial.org videos, because spokentutorial.org was a very frequent term in the training data. So we thought that it might be the same domain. And to obtain the final model, we trained a language model for each data source. So we trained a language model for the training data, for the CommonCrawl data, and for the English subtitles. And then we just interpolated these models into the final model. So let's look at the results. When we have the baseline model, the mapped phonemes seem to work slightly better. And then when we do training data cleanup, which was very important, this is an issue that was raised by our colleagues from JHU that found that the data is really noisy. And I think that Sanjeev is going to talk about this more in his talk. The cleanup was really important for this task. And we also found that resegmenting the test data also seemed to help because the provided segmentation wasn't great. And finally, incorporating the web language model data and other language model scoring further helped with the word error rate. So these were the results for Hindi English. And we saw a similar trend in Bengali English, except for the RNN language model scoring, which didn't work. And we believe that this is because of the language model data that we used for Bengali. So to conclude, in both challenges, or both subtasks, we managed to place first. And so this shows that ASR model for low resource languages can be trained with standard Kaldi recipes and crawl text audio data. We also showed that confidence-based language identification works well, but it would be unusable in practice, so we need to replace this with something that will make the decoding more efficient. And cross-angle phoneme matching can be learned automatically using automatically crawled Wikipedia data for languages using different scripts. So on one hand, I'm happy that our approach won the challenge. But on the other hand, I'm quite sad that this naive approach can win this challenge. So I hope that in the future, we will have better systems for this. Thank you for your attention.
So thank you for your talk. Do we have some questions?
Okay. Can the speakers come to the front, pick the microphone, the people who want to ask questions come to the front and raise the question in front of the camera. So the microphone is on the chair over there. Sorry, I should have explained that.
Hi. Does it work?
Yes.
Okay. Do you have any more information about this phoneme matching? So did you encounter any phonemes that would match, or because the phoneme systems are obviously very different, do you have any statistics of how those phoneme sets work together?
No, we didn't do any analysis of this because this was implemented in one afternoon. So, so we just wanted to get some performance gains. We didn't do any analysis of the font.
Very nice talk. I know that if you're looking at South Indian languages, Marathi, Kannada, Telugu, and so forth, in most of the regions in India, they're spoken in each kind of state, so to speak. But near the borders, they speak hybrids that are blending between these two, which makes speech recognition incredibly difficult. Did you take into account any of the geographical or the maybe potential cross-language blending that might take place?
No, I think this is a good question. I think in the future we should look at this, but this approach was purely data-driven, so we didn't have any linguistic knowledge of Indian languages. Thank you.
Yeah.
If you go back to your last plot, the bar plot, I guess, this one. This one. I understand here that the phoneme mapping doesn't make that much sense. Yeah. So do you say it doesn't matter how the lexicon looks like as long as the LM is okay?
Yeah, I think it might be the case. Also, one thing that I think that Sanjeev will mention is this evaluation was also a bit complicated because there might be words written in Hindi script and in the English script, and they might be considered as two separate entities. So the scoring might be affected by this. So I think to get better idea about your question, we would need a different scoring mechanism. Thank you.
Yeah, thank you for this interesting presentation. I have a question about the language ID you did on slide 6. So the last step was, if I remember correctly, that you included speech rate.
Speech ratio.
And first question, how did you obtain that? And did you also consider using the language ID distribution as a prior to include also the recognition scores in the different languages?
Yeah, so the speech ratio is computed by taking the total duration of decoded words divided by the duration of the segment from the VAD segmentation. We don't know why it works, but it works in this case. And we tried using X vectors for this, but this seems to be more robust. Thank you.
So actually, can I dig a little bit deeper into the speech ratio? So did you combine the scores with a model, or did you use two thresholds to make the decision? Or?
So if I can go back to slides, please. Yes, so confidence is in the interval of 0 to 1, and the speech ratio is also in the interval 0 to 1. So we just add them together and divide it by 2.
Okay.
And now if you look at the plot, the dots that are above the diagonal line are misclassified. So it was just a winner takes all approach.
Would you expect that if you train a model that combines speech ratio and confidence values would perform better than using this obviously simple but working heuristic?
I think that speech ratio is a hack, and I think more principled approach should be used.
So speech ratio was used as a feature in confidence estimation before. So that's, I think it might be something useful, especially for LID, because if you have a speech recognition output on a speech recognizer run on the wrong language, the alignments are totally off, right? So I think this might. Do you think that might be an explanation for why it actually works?
That's what we saw. Yeah.
Okay. Yeah. Okay. Let's see. Do we have more questions in the audience here, or? Oh, we have a question in the chat. Okay. This question is from Ibrahim Al-Marjai from Huawei. Also, you have the same phonemes across languages. The phones differ in their acoustic properties. For example, the phonetics of retroflex sounds differs between Dravidian thank you, and Indic languages. How do you think it would affect the training of the multilingual acoustic model?
Yeah, so because each language might have different phoneme set, we used different target or output layer for each language. So only the feature extractor was shared among languages, but the output layer was language specific. So I think that's
okay. I hope this answers Ibrahim's question.
Yes, so I think we have time for the last question. Is there any? If not, I would think
yeah.
was speaker.
Thank you.